In this video, we will explain the physics behind circular motion, teach you how to calculate the various forces in circular motion, and define some important vocabulary on the subject. A satellite orbits the Earth in a circular path because of gravity's force pulling it in. If the Earth suddenly disappeared and there was no longer any gravity affecting it, which way will it go? Will it continue its circular motion or go straight?
Well, I'm not sure, but I'd guess that the satellite would continue curving in a circular motion for a bit because it has the spin and velocity of a curving object. Maybe after a little bit it would go straight because the spin would wear off.
While that is a good guess, the satellite would actually proceed in a straight line without gravity. This has to do with the lack of centripetal force and acceleration on the satellite. Newton's first law of inertia states that an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. And naturally, inertia wants the satellite to continue in a straight line. Look at the velocity of the satellite. Everywhere on its path, its instantaneous velocity is a straight tangent line. The only reason the satellite, and any object in uniform circular motion for that matter, curves is because of the centripetal force, which in this case is gravity. The centripetal force causes what we call centripetal acceleration, which is what causes the satellite to move off its natural path and into a circle. So when Earth and its unbalanced force of gravity is gone, according to Newton's first law, the object will keep traveling in the same direction and speed it is going at that instant, or its instantaneous velocity. As we know, the instantaneous velocity is a straight tangent line, which means that the satellite will travel in a straight line in the absence of gravity's centripetal force and acceleration.
Oh, okay. Well, that makes sense. So in terms of solving for variables, I imagine that it is simply a matter of applying the equations of motion to this particular pattern of motion, right?
Yeah.
Well, if I may, I think I can explain that.
Of course, give it a shot.
So the period, or time, it takes to complete one rotation can be found using the basic equation for time. Time equals distance divided by velocity. In this case, the distance of one rotation will be the circumference of the circle, 2 pi r. For example, if the circumference was 20 meters and the object was going 5 meters per second, I think it would take 4 seconds to complete one rotation.
Yep, that's right. Now try solving for speed.
Well, the equation for average speed is distance over time. So in this case, distance traveled is again the circumference. So speed is 2 pi r divided by time.
Good, but how about solving for centripetal acceleration?
You're going to have to do that one.
Okay, so first off, remember that centripetal acceleration is a center-facing acceleration that makes an object move in a circle. Unlike our typical idea of acceleration, the centripetal kind changes the velocity of an object, but not its speed. This is because velocity indicates speed and direction, and centripetal acceleration only changes direction. Centripetal acceleration is going to tell us how the velocity vector changes each second. Centripetal acceleration equals velocity squared over radius.
So to sum up what we've learned today, objects will only travel in circular motion if there's a centripetal force applied to them. And you can use the equations of motion to calculate variables related to circular motion as well. And if you have any questions about how this makes sense, be sure to check out the reading on circular motion for CK12.